Now, we pay our attention to cylindrical polar coordinates. This is merely an extension of polar coordinates in R2. Now, this system is important, this coordinate system is important when we are dealing with cylindrical objects. Okay. Now, if you take this diagram, if you consider this diagram, you can locate a point in R2 on xy plane where the distance from the origin to the point is rho and this angle is theta. It is exactly the polar coordinate system. Now, if you have any point in the space P, right, you project that point to xy plane and then you write this point on xy plane in polar coordinates, right. If you have any point P in the space in R3, you project that point onto xy plane. Now, the point you get after projection, you write that point in terms of polar coordinates. So, if the distance is rho, this is theta. So, x is rho cos theta, y is rho sin theta as in polar coordinates, and the third coordinate z is simply z. So, the relationship between rho theta and z are given like this: x is rho cos theta, y is rho sin theta, z is z. Again, let me tell you what it is. If you have any point in the space, you first project it onto xy plane, then express that point, because since it is on xy plane, you can express it in polar coordinates, right. So, if the distance is rho and this angle is theta, this is rho cos theta, and y is rho sin theta, and z stays as z. Now, if you look at the directions along which you change only one variable, like if you take rho, if you move along this line segment further away from the origin, rho increases, but theta remains fixed and z is 0 fixed. Therefore, if you move along this direction, you can simply change rho without changing the other two. So, that is the unit vector along that direction. Simply like in the polar coordinates, without changing the value of rho as well as z, you can increase theta by moving along this direction. By keeping the same radius, you can further move this way on xy plane without changing rho and z. By doing so, you simply increase the value of theta, and that is theta hat. Theta hat means the unit vector, or theta hat stands for the unit vector along which theta increases while rho and z remain intact, they do not change. Now, on the other hand, if you take z, right, at this point, let me project these vectors up. This rho hat, theta hat is in this direction, and if you want to increase z without changing the other two variables, you have to go this way, right, that is z hat. Now, if you write the same diagram here, you have it here, right, this one. For the sake of clarity, let us write it again. Now, if you compare it with XYZ system, now this is how the right hand coordinate system persists, like from x to y, right. If you take a screwdriver and rotate in this direction, the head moves in this way, the handle moves in this way. So, that is the third axis. So, we call it as XYZ system. From x to y, you rotate a screwdriver, the handle goes in this way. Right, that's the from the first and the second coordinates, coordinate axis, you can get the third one. Similarly, from rho to theta, if you rotate in this direction, if you take a screwdriver and rotate in this direction, it moves in this way. That is z hat. So z should be the third coordinate. Rho should be the first, like in the xyz. Theta should be the second. Z should be the third. Now, after that, let's try to find the infinitesimal or the volume of the infinitesimal element. Now, as I told you earlier, this is merely an extension of the polar coordinates. So, in polar coordinates, you know that when you have rho, you give a little increment in rho hat direction. So, this delta rho, this angle is delta theta. Now, you know what this is from the arc length. This arc length should be rho times the angle d theta, sorry, delta theta. And if you project this up, you have the same shape. If you project it onto a horizontal plane, you have the same shape. Now, you give an increment to z, that is dz. So, you have the object like this. Again, if I want to write this, you get some, no, I think I don't need to do it. This delta rho, this one, this length is from the arc length, you know that radius times the angle, rho delta theta. This should be, I write delta theta, rho delta theta. This delta rho, this height is, I write delta z, delta z. So, the volume should be what? Volume should be rho delta theta, then this length is this like a cuboid, delta rho delta z. Now, as delta rho goes to 0, delta theta goes to 0 and delta z goes to 0, you can replace them by d theta, d rho and dz respectively. So, if you multiply them like this is the volume of the infinitesimal element. That is how it should appear in the integral. Okay. Now, we will do an example using cylindrical polar coordinates. Now, find the mass of this object. This is a portion of a cylinder, right? It is only in the first octant. Radius is 2, height is 3, and it is this angle is only 90 because it is between x and y axes in the first octant. So, it should be 90 degrees. The density is given by this one, this expression. Now, the volume of the infinitesimal element is this, as we saw up there. The volume of the infinitesimal element, you have like dx, dy, dz or delta x, delta y, delta z. You have those product of those deltas, but you get a scale, some multiple there, some you get rho. So, rho times the product of these three, all right, you have this. But that is the volume of the infinitesimal element. Now, we need to find the mass. When it comes to mass, we have to multiply it by its density. So, this is the density at a given point. So, density times the volume gives you the mass of the infinitesimal element. Now, this is a little mess because we have all 4 variables in the expression. So, we need to replace x and y by rho and theta. So, this is how we do it. We know that we saw it earlier. Again, let us go back to where we first introduced the cylindrical polar coordinates. So, x is rho cos theta, y is rho sin theta. It is the same as polar coordinates, but z is z. Now, you can see that I replace x by rho cos theta. So, you get rho squared cos squared theta. Here you get rho squared sin squared theta. When you pull out rho from these two, You get cos squared plus sin squared, which is 1. Then the square root of rho squared is rho. So, this 1 plus rho, this whole thing is equal to rho. You have one rho left out. So, it is this, and that is what you get as the volume of the infinitesimal element, sorry, mass of the infinitesimal element. Now, what are the limits? When we want to find the total mass, definitely you have to go through a triple integral. So, we need to know the limits of these variables. You know, rho is the, in this area, in this volume, rho goes from 0 to 2. So, that is what I have indicated here. In this volume, rho goes from 0 to 2. The maximum distance you can achieve is 2. The maximum height you can achieve is 3. So, Z, limits of Z are from 0 to 3. It starts from 0 from xy plane up to this point, this plane. So, the limits are from 0 to 3. Then the angle varies from 0 to 5 by 2, because it is between xy axis here. So, angle varies from 0 to 90. So, it is there. Now, total mass, let this volume be V. So, in V, that is why I have introduced the V there, without exactly indicating the limits. In V, this is what you have this is what you have for the mass. Now, let us assign the limits. Limits of rho from 0 to 2, limits of theta from 0 to 5 by 2 here, limits of Z 0 to 3. Now, you can integrate this one. You have rho squared over 2, rho cube over 3, assign the limits. After that, once you assign limits, you know rho is equal to 2. So, 2 squared over 2 is 2, 2 cube is 8, 8 over 3, which is 14 over 3. Now, we introduce a pair of braces just to make it little clear. Now, the variable of integration is theta. So, you can go back there. This is a constant, 14 over 3 times theta, right, 14 over 3 times theta. Then the limits of theta are from 0 to 5 by 2. So, 0 to 5 by 2. Now, when you plug in 5 by 2, you will end up with this one. When you plug in 0, it is 0. So, you can ignore that term. So, this is what you get. After that, it is a simple integration. You simplify it, then integrate it. Variable is Z. Now, you plug in the limits 0 to 3. So, first you plug in 3, then you plug in 0. You will end up with 75 kilograms. Okay, thank you.